So two-body problem. We started discussing it in the previous class, and I hope to finish it today. So where we finished? You remember we massaged, we made a deep Swedish massage to that Lagrangian, right? In order to simplify, and so we had like 5 versions of the Lagrangian. So eventually we ended up with this Lagrangian. Okay, yeah, I can write it. So L equals 1 over 2 mu. Mu is the reduced mass, you remember, right? The reduced mass. Then r dot squared plus r squared phi dot squared and minus u as a function of r. Beautiful Lagrangian in terms of simplicity, right? Okay, probably I should frame it because, yeah, once you have Lagrangian, the rest is a question of calculus, right? Not a physics. Okay, so and then, so first of all, effectively, it's a Lagrangian of a single particle. So we started with 2 particles and we ended up with the single particle. Magic of math, right? Of mathematics, right? So first Lagrange equation. So we wrote down dl over d phi equals to d over dt partial derivative of L with respect to phi dot, and we ended up, of course, phi is cyclic, so the corresponding generalized momentum, in this case angular momentum, was conserved, and we wrote it down. So L, that constant, it's what, mu r squared phi dot, mu r squared phi dot. And as the last piece of the previous class, I wrote down, solve it for phi equals L over mu r squared. Okay, let me frame it in blue because I will need it several times in today's class and I want to keep it right. Okay. So now the second equation for r. Right, so partial derivative of L with respect to r equals to the total derivative out of partial derivative with respect to r dot. Of course, let's do it. So with respect to r, we will have mu r phi dot squared. So mu r phi dot squared, right? And this r dependence minus partial derivative. Okay, yeah, strictly speaking, it should be partial derivative. But since our potential energy is a function of one variable, so let me switch immediately to a straight derivative. And guys, I noticed that some of you kind of, in your homework, a little bit sloppy in terms of these partial derivatives, these curvy derivatives and straight. No, guys, keep track of them because it's very important, partial or straight derivative. But in this case, it doesn't really matter, so let me switch to a straight derivative. du over dr, right? And equals to, this will give us mr dot and another dot, so we will have mu r double dot. Okay, cool. Now let's combine these 2 equations. I will just take this phi dot and plug it into the second equation, right? And as a result, we will end up with mu r double dot. So we will have L squared, 1 mu downstairs, and r to the power of, okay, 4, then 1 gets cancelled, r to the power of 3. So it will be equals to L squared over mu r to the power of 3 minus du over dr. So that's what we're getting, right? Second order differential equation. Right. And of course, this du minus du over dr, it's an actual force acting. Of course, it can be force of gravity or electric force, right? Something like this. So this is actual force. Maybe I should immediately write it down. Yeah. So this is so it's a F, and let me write, it's that actual force acting on the system. This term, okay, maybe I should write it separately. This term, no, let me save space. So this, the first one, we can call it centrifugal force. But of course, it's kind of fake force because what is really inside of that? It's a hidden motion in the phi direction, right? Okay, so let's call it centrifugal force. So F sub CF, subscript CF, centrifugal force, right? So it's called centrifugal force, right? Okay, so now, of course, we can write it as actual force F plus L squared over mu R to the power of 3. Okay, so that's the equation which we need. And you know what? Let me frame it. And we will get back to this equation maybe like in 5 minutes. Okay, 7 minutes. But for now, let's digress. Let's just leave it alone. And let's look at let's rewrite this equation in order to have some kind of energy approach to analyze behavior of a system. Sort of, let's digress a little bit. So let me check if I mention everything. Yeah, okay. So now let's digress. I will put a new bullet. So let's digress a bit. And then again, we will get back to this equation, second order differential equation. So which way? Let me get out of this d over dr out of some potential, right? In order to combine, so that we combine this centrifugal force with the actual force, right? So let me do this. All right, maybe I will write separately. So L squared over mu R to the power 3, we can write it as d over dr minus L squared over 2 mu R to the power of 2. Let me check. If we differentiate, 2 will get cancelled, minus disappears, and R to the power of 3. Yeah. And this construction inside, we can call it, okay, let me insert it, and then I will call it. I will give a name. So we can plug it here. So we will end up mu R double dot equals minus, I will take outside, right? And d over dr out of u plus this L squared over 2 mu R to the power of 2. So we combine these two terms now. And now we can introduce, no, before I introduce, let's call this term. This is the actual potential energy, right, associated with this actual force, right? For example, gravitational potential or electric potential. This term, of course, we can call as centrifugal potential, right? Centrifugal potential energy, right? So let's call it. So L squared over 2 mu R power of 2, it's a centrifugal potential energy, PE, potential energy, right? Okay, and now we can introduce what is called effective potential. This whole construction, we can call it as U effective potential energy. It's a very clever idea, very useful idea when you want to analyze behavior of the system conceptually, because what we're getting effectively now, mu R double dot minus equals to minus du effective over dr. Look at this equation. It's equation of a one-dimensional system of particle, right? And basically, which depends only on R. So it's a one-dimensional problem, all right? And you remember chapter 4 when we spent tons of time, okay, not tons of time, plenty of time analyzing systems like this. And you remember, second remarkable feature, if you plot potential energy versus position, you can analyze behavior of the system qualitatively, right? Basically free of charge, right? Basically making the very small amount of mathematical manipulations, right? But very often it's okay, practical, useful, easy, reasonably easy, and lots of problems in books, right, on the qualifier exams about this effective potential. The idea was that you will introduce effective potential, analyze the system, right, and so on. There will be also one problem, I think one in your homework. I will have to post it actually, right? Okay, so now let me write it. So it is effectively 1D system. And as I said, we can use the second remarkable feature which we introduced in chapter 4. Right, so let's use, okay, maybe I will write underneath. Right, so we can use the second remarkable feature from chapter 4. If you plot, as I said, potential energy versus position. But of course, in order to do that, as for example, right, we need to say which actual potential actually acts in this system. Let's assume that gravitational potential, because after this we will actually move to the gravitational case, and we will prove Kepler's first law. Okay, so now, so I'm still here in this digression. So let's use u, right, of course it's a function of r, equals minus g m1 m2 over r. So gravitational potential, of course, minus indicates that, of course, it's a force of attraction. Of course, if it was a Coulomb potential, of course, it will be without minus. Okay, now what we're going to do, we're going to write this in terms of, okay, I will probably use color. Effective, reduced mass, right? Because in our equation we have mu, which is reduced mass. Inside of this mu we have m1, m2. And here we have m1, m2. Let's just rewrite it in terms of a reduced mass. And in terms of reduced mass, this is equal to reduced mass times the total mass. You can easily show it. Right? And so, as a result, the effective potential energy, so U effective, you know what, let me move slightly closer to this, because I need some space. No, I doubt that I will be able to fit. Okay, we'll see. So U effective, every time I have to think about space. Do I have enough space, right, on the whiteboard? So will be equal. So minus G mu M over R, and where is my centrifugal? Okay, here. Plus L squared over 2 mu R squared. Okay, so that's the effective potential energy, potential energy, not potential. And so now if you plot it, okay, I think I will be able to fit. At least I will try. So let's say this is energy, all right, then this is R, right, and so this is negative potential energy. So if you plot it, of course, it will go something like this. Let me use blue. So that's this gravitational potential energy, and centrifugal potential positive and decays as 1 over r squared. So if you plot it, you will get something like this. So this is proportional to 1 over r squared centrifugal potential. So if you add them up to plot effective potential, of course, you will end up with something like this. So that's our U effective, right? Yeah, and now you can analyze its behavior. So, of course, it depends on the total amount of energy that you provide to your system. So if your energy, okay, maybe I will use, yeah, let me use black. So if you provide this amount of total mechanical energy, so that system can exist only at that point, R will be fixed. So it means that orbit is, because we still have a hidden phi motion, R is constant, but still we have a hidden phi motion, and phi of course changes. So if you provide this amount of total mechanical energy, E1, of course you will get circular motion. Okay, I will write underneath, and it's getting more and more difficult to write. So circular orbit. So basically, you see, without spending too much time solving the problem, you can get information about orbits conceptually, right? If you provide this amount of total mechanical energy, you will have two turning points, R minimum and R maximum. It's an elliptical orbit, right? So if you provide this amount of total mechanical energy, of course, you will get elliptical orbits. If you provide this amount of total mechanical energy, E3, basically it's equal to 0, you'll get a parabola. So parabola, okay, parabolic orbit trajectories, right? And of course, if you provide this amount of total mechanical energy, now it's E sub 4 positive, then you will have only, also like in a parabola, only one turning point, right? So in this case, hyperbolic motion, hyperbola, right? So you see, yeah, we can easily get some information about the motion basically free of charge, right? Without any significant amount of mathematical work. So yeah, this effective potential is very useful. Right, so now, of course, at those, maybe I should emphasize, at these turning points, all of them turning points, R dot equals to 0, right? R dot equals to 0, and these are turning points. Turning points. Okay, at this point, we should say, okay, enough about this digression, right? So the idea was to introduce this effective potential energy and show that we can analyze behavior of the system. So now, enough of digression, and we need to go back to our second order differential equation. Let me label it maybe something like 1, right? And now I will write. So let's go back to equation number 1. Right, so now go back to 1 and solve it. So now, yeah, we need to solve everything rigorously and get these trajectories, right? Not just conceptual analysis. So you know what? I will rewrite again one more time these differential equations. So mu r double dot equals to, okay, I will use the force plus L squared over mu r to the power of 3. Okay, I will again frame it. Right. And so now, this equation can be solved for two answers for two pieces of information. So first option, let me put, okay, probably I will write, it can be solved for, okay, and option number one, you can solve it for r as a function of time and phi as a function of time. It can be useful if you are actually interested in the history, how r changes with time and phi changes in time. And of course, in this case, you can easily get the velocity r dot and phi dot. So sometimes this can be useful for your analysis, for your applications, whatever, right? But there is a second option. Right, second option, you can solve this problem for explicit dependence between r and phi, basically for a trajectory. And most of the time, people are interested in a trajectory. So, trajectory. So we are interested in the second case, right, in the second situation. Right, look, and this equation, this second order differential equation in this form fits well to solve for option number one. Why? Because we have r double dot. What r double dot? It's a second derivative of r with respect to time. So you just grab that equation, solve it, and you should be able to get this. That equation, I mean that solution, right now, you cannot get from that equation. So you have to modify that equation. You have to change it. In which way? You have to replace this second derivative with respect to time. You need to replace it with the second derivative with respect to what? Phi. So that you will get actually equation, differential equation, and the solution of that equation will be this, right? So again, this can be obtained from that equation. And in order to get this solution, we need to modify our equation, right? So let's do it. First, I will write, so we want this. We want this, right? This option. And so in order to get that, let's modify it. Right. So we need to, okay, not change, but modify the equation. And let me show you which modification I want to do. First of all, instead of r double dot, which is, again, as I said, it's a second derivative of r with respect to time, we want first replace t with phi. So we want to get, which way I wrote it? Just a second. Okay, just second derivative of r with respect to phi. Right? So it will be sort of like a r double dot. And it's not enough. In order to make the equation the most pleasant in terms of a solution, we will have to replace this r with a reciprocal, with 1 over u. Right? And then we're going to replace u as 1 over r. And then, of course, we will get the equation, the derivative, the second derivative of u with respect to phi. Again, this substitution we need in order to make the equation better. Right? So we will do it now. So first, I just wanted to outline what I'm going to do now. And now let me actually do that. Okay, let me check if I mentioned everything. Yeah, it looks like. So now, actual massage. We need to get dr over d phi. Let's start with dr over d phi. Okay, we decided, so we're going to replace. Yeah, okay, let me start. Let me emphasize that, of course, u, it's a 1 over r. And so let me write du over d phi. So I'll start pretty much from the end. So it's a first derivative, and then of course I will, the result of this, I will differentiate one more time in order to get this derivative. And we will extract from there r double dot and plug it. You will see everything will be fine. So it's a d over d phi out of 1 over r, because u it's a 1 over r. Right, 1 over r. Okay, so let's differentiate it. Of course, we will get minus 1 over r squared and d r over d phi. Right? And now let me squeeze dt into this derivative. So we will get minus 1 over r squared and dt over d phi and dr over dt. You see, if you cancel dt, you will get exactly the same. But now we have r dot, and if you take this dt downstairs, you will get phi dot in the denominator, right? Okay, let me write it just to be safe. So 1 over r squared, r dot, and downstairs we'll have phi dot. And phi dot, we're going to use this. That's why I framed it, because I knew that I would need it at some point. Okay, let me emphasize that what I'm going to use was using my explanation box. So phi dot equals to L over mu r squared. Okay, so if I plug it there, r squared will be cancelled. Right? Should be. Yeah. Okay, anyway, let me write it. So 1 over r squared. Then L will be downstairs, upstairs, mu r squared and r dot, not r double dot, 1 dot. So r squared goes. And as a result, we have minus mu over L r dot. Okay, so we got here we have u prime derivative with respect to phi, and here r dot. So let's differentiate with respect to phi one more time. And then on the right hand side, we will get r double dot. So now second derivative of u with respect to phi, so it will be d over d phi out of what we got, minus mu over L r dot. And I'm going to do the same manipulations. Okay, first of all, constant, of course, I will pull it out. And I'm going to do the same manipulations like I've done here with dt. I'm going to insert dt into this derivative. So, but first, constant outside, mu over L, and then dt over d phi and d over dt out of r dot. Again, you see constant outside, and now I inserted dt. So we're getting r double dot. And again, phi dot downstairs, like over there. So I'm going to use this one more time. And so as a result will be minus mu over L. Then instead of this, phi dot, again, L will be downstairs in the denominator and mu r squared in the numerator, right? So that's dt over d phi and r double dot. Right. Okay, let me simplify it slightly. Mu squared, r squared. You know what? R squared, we're replacing it with u. So let me get rid of r squared and introduce u squared in the denominator. Okay, let me do it immediately. So it will be L squared, U squared, and R double dot. Okay, so now let's solve it for R double dot in order to insert it in our differential equation. Right. So, of course, from here, R double dot will be equal. So it will, and instead of this, okay, let me write. So I don't want to write this complicated. I will just use U double prime. Right. Again, prime derivative with respect to phi in this case. So, oops. So L squared, U squared goes up there. So it will be minus also there. So it will be minus L squared, U squared over mu squared, U double prime. So that's what we want. So we replaced derivative. So now let's put it into that differential equation. So as a result, mu and minus L squared U squared over mu squared U double prime. So left-hand side, and then F. Of course, F now will be a function of U, because whatever the force you have in your problem, you can replace R with 1 over U. So you can easily write it as F as a function of U, and plus our constant L squared. No, not the constant, centrifugal force. But again, R will be replaced with U. So U to the power of 3 will appear in the numerator. Mu and U to the power of 3. Okay, so now let's get rid of this factor in front of U double prime. So we will get U double prime equals. So we're going to multiply this whole equation by mu and divide it by L squared U squared with minus. Right. So the whole equation by that, right? Yeah. So this term is going to give us mu gets cancelled, L gets cancelled, only U will be left with minus. So it will be minus U. And this, yeah, minus mu over L squared U squared, and the force as a function of U. Cool. That's what we, okay, let me first check. Yeah. So that's the equation which we need to solve for this option. So again, that equation was awesome for that solution, to get this solution. And now, in order to get the second option, trajectory, that's the best form of this equation. And so what, there are two types of problems which can be solved using this equation. First, if you have explicit form of the force, you can get trajectory. Right? That's the first problem, a type of problem. The second, if a trajectory is given, for example, you know how you observe that something is behaves somehow around another object, right? Let's say trajectory is given. So you can plug U trajectory into this equation as a function of phi and get the force which created that trajectory. Right? So there are two types of problems. In your homework, I think there will be both of them. So two possible situations. So let me write. So now we have two possible situations. Two possible situations. So the first one, okay, probably I will write underneath. So the first problem, F is given, F is given, and of course you need to get a trajectory. So R equals to R as a function of phi. So one problem. And of course the second, R as a function of phi is given. And you need to get the information about the force. Actually, that's what happens in scattering, right? That's what we discussed that in the graduate level course. But effectively, it's that, right? So you send the particles, you scatter them on some object which you want to analyze, right? So you observe a trajectory, and then using this equation, you can get the force which that object exerts or creates around itself. Yeah, so that's for scattering situation. For scattering problem, all right, so given, and then you can get force as a function of r. Because that's what most of the time people try to achieve using scattering. Okay, so once we got the equation, now what's left? We just need to take some force, for example, and solve it. And of course, we're going to take a gravitational force in order to solve Kepler's problem. All right, so we're going to prove Kepler's law number 1. Right. Okay, so I think I don't need this. The equation is over there, so I can erase all that. So now, okay, this section, let's call it Kepler's orbit. Basically, now we're going to start solving this differential equation. We're going to start solving, of course, assuming that you have force of gravity acting on our fake particle mu of reduced mass. So let me title it the Kepler's orbits. At least that's how book calls it, right? Kepler orbits. Okay, so let's use force F, okay, as a function of r equals minus g, okay, which I use m1, m2, yeah, minus g m1, m2 over r squared. Right? Again, who wants to drag those constants? Let's hide them under gamma. Right, so let's introduce gamma equals to, I think it was minus. Oh no, minus I kept outside. G m1 m2, right? So as a result, force and of course, since equation is written in terms of u, so of course we need to get rid of r. Again, let me remind you. So of course, r equals to 1 over u. So as a result, force F as a function of u will be equal minus gamma u to the power of 2. Right? Yeah. Okay, so now plug it in differential equation and see what we can get. Right, so as a result, u double prime equals to minus u minus mu over L squared u squared and minus gamma u squared. And now you should be able to see the beauty of this force. The equation gets simplified tremendously in the case of this force of gravity or electric force, because this u to the power of 2 gets cancelled. And as a result, we're getting this just a constant. This term will be just a constant, and the equation becomes trivial. Right? So now equals to minus u plus mu gamma over L squared, right? Yeah. And it's the nicest equation you can think of. Of course, it's still second order inhomogeneous differential equation because we have free term. Of course, strictly speaking, you should find a general solution of homogeneous equation, then find any particular solution of inhomogeneous equation. You remember the end of chapter 5. But here it's not worth of those troubles. We can solve this equation easier using very simple mathematical tricks, which you can easily see that. Okay, so let's rewrite this equation in this form. Okay, let me start with equal, with the middle of the equation. And first, let me adjust this side. I will write it in this form. I will put minus outside and I write u minus gamma mu over L squared. So, u minus some constant. Since on the left-hand side we have a derivative, second derivative, so we can write also in the same, we can create also the same form, u minus gamma mu over L squared, second derivative. Because constant will disappear. So this equation and that equation are exactly the same, identical. But now we have exactly the same structure here. Let's call it W, for example. And here exactly the same, also W. So we're getting a very, very simple differential equation, which is W double prime, sounds so funny, minus equals to minus W. Trivial differential equation. It's effectively, it's a simple harmonic motion equation, right? Okay, let me remind. So it's similar to, you remember, x double dot equals minus omega squared x, and you remember the solution was, of course, let's use again cosine shifted, phase shifted cosine solution. I think that's how it's called. Every time I get confused about that. Okay, x equals a cosine omega t plus or minus. I think we use minus here. We use minus in this book, minus delta, right? So it's a similar to this. So, but now in our case, what is omega? Just 1, right? And then here we have second derivative with respect to time. So as a result, we have t here. But in our equation, we have double prime. Those are derivatives with respect to phi. So in our solution, instead of t, we're going to have phi. Otherwise, it's exactly the same. So we can write w as a function of phi will be equal some constant a, constant of integration, times cosine. Again, instead of omega, our omega is 1. So it will be just 1. And then instead of t, phi, and minus constant, second constant of integration. So that's the solution for w. So let's go back to u. Okay, let me check if I... Okay, you know what? Before we go to u, yeah, that's why I looked at my notes to make sure that I make that switch at the right time. This constant delta, constant of integration, it's basically the value of phi angle. You remember? It's just an angle in polar coordinates. It's just a value of phi at the initial moment of time. Basically, it is phi naught. Okay, let me emphasize that. This is effectively just phi naught. Okay, so we have a freedom to slightly adjust coordinate system if we feel like, right? So let's assume that we adjusted our coordinate system slightly. What if we turn it by phi? In that case, this constant will be 0. Initial phase, of course, in this case, it's initial angle, will be 0, right? So let's assume that we turn our coordinate system. Okay, let's turn our, our coordinate system to make delta, which is actually phi naught, 0. So as a result, we will have just A cosine phi. Right? And now after this, we can go back to U. Right? So as a result, U will be equal. So it's a W, so U, W plus this constant, right? Right? Yeah, of course. So it will be A cosine phi and plus that constant, gamma mu over L squared. So now that's the solution for U. And again, U, you remember, it's 1 over R. Now, once we solve differential equation, now we can go back to R, because when we analyze problem, who wants to analyze problem when your variable, okay, U is a reciprocal of R? No, of course, it's much easier, much more convenient to work with R at this point. Once you solve differential equation, the role of U is done. And so now let me rewrite this slightly different way. So first, U equals, let me factor out this gamma mu over L squared. So it will be gamma mu over L squared, and we will have 1 plus A L squared over gamma mu cosine of phi. Okay. I just factor out that constant. And now it's time to start introducing constants. Now we're going to introduce tons of constants. You will feel dizzy at some point. So let's start. First, this, let's call it as 1 over C. So effectively, we can introduce the first constant. I'm thinking, where should I start writing them? Okay, let me write it here. So first, C equals 3 lines by definition. It will be L squared over gamma mu. L squared over gamma mu. So it's a first constant, which we introduced. The meaning of these constants we will see maybe in 15 minutes. Right? Okay, now the second constant. This construction, let's call it epsilon, eccentricity. And this actually dimensionless. You see, it should be dimensionless because we don't have units here. This is also dimensionless, so this must be dimensionless. And it's called eccentricity. So epsilon equals, again, 3 lines. So it's A L squared over gamma mu, and it's called eccentricity. So that's second constant. And again, U, it's 1 over R. So let me rewrite. So 1 over R equals, so this is 1 over C and 1 plus eccentricity times cosine phi. Okay, so now let's just make the final push. Just flip it. So R equals C divided by 1 plus eccentricity times cosine phi. So that's basically the final form of the, that's our trajectory. You remember what we're trying to get? We're trying to get this, R as a function of phi. Not trying, we already got it. Ta-da, here it is, enjoy it, right? So that's our trajectory. So that's our trajectory. Basically, it's an equation of conic section, right? You remember? Okay, I don't know where you study, in which course you studied that here, but when I was in Ukraine, we had a special course, analytical geometry, and there was a big part of that where we analyzed second-order curves, which are circle, ellipse, parabola, circular, right? Canonical coordinates, not canonical, lots of analysis, right? So conic section, equation of a conic section. So let me write. So it's an equation of a conic section. You remember conic section. If you take, maybe over here I will okay, let me remind it here. So if you create, okay, if you draw a cone, sort of like this, oops, like this. So if you start creating sections, if you create section in this direction, of course you will get circle, right? If you at a small angle like this, or maybe let me draw it in this the upper part. It doesn't matter, but all right. So if you draw it like, if you create a section in this direction, of course you will get ellipse. If you create a section parallel to this line forming the cone like this, you will get parabola. And of course, if you create a section this way, you will get hyperbola, right? So that's what I mean by conic sections, right? Okay, I'm not writing it. You should remember that, of course. I'm just reminding you. Yeah, and of course these are called second order curves. Now, next, of course, inside of this, as I said, there are all circles, ellipses, parabolas, hyperbolas, and it all depends on the value of epsilon, the value of eccentricity. If eccentricity equals to 0, it's a circle, right? We will get that. Then if eccentricity is less than 1 but larger than 0, you will get ellipses, right? If it's epsilon equals to 1, you will get parabola, and if epsilon is larger than 1, hyperbola. So let's start with bounded orbits, and epsilon is between 0 and 1, 0 included. Okay, so I think, yeah, we have an equation. We already got the solution, so I can erase all that. So let me label it bounded orbits. So let's put a new bullet, and let's discuss first bounded orbits. Of course, you understand that these are circles and ellipses, right? Bounded orbits, and eccentricity, which is very important. Eccentricity now is larger or equal than 0 and less than 1. So for this, okay, and I will, of course, rewrite let me rewrite it one more time. Our answer, C1 plus epsilon cosine phi, because at some point I will start erasing this. So I want to have that there. So first of all, let's show that under these conditions, with this epsilon, we're going to get actually bounded orbit. Let's find our minimum and our maximum, right? So our minimum is when denominator is maximum. Denominator is maximum when phi equals to 0, right? In that case, cosine is 1, and denominator is maximum, and of course, r will be minimum. So when phi equals to 0, and of course, it will be equal to C1 plus epsilon. So we have a minimum value. Now let's check the maximum value. So r max, of course, our maximum is when denominator is minimum. So minimum when cosine is negative. Cosine is negative when phi. So phi equals to pi, and it will be equal to C1 minus epsilon. So cool. And of course, epsilon is less than 1, so it doesn't blow up the value of our maximum. So both of them finite. So we have our minimum, our maximum. So as a result, yes, we have a bounded orbit. So yes, it does work. Then, of course, for a solar system, our minimum is called perihelion, and our maximum is called aphelion. maybe I should mention it. Right, okay. For a solar system, R minimum, it's a perihelium. Oops. And R maximum, of course, is called aphelium. Right. Okay, just a terminology. It's not a big deal. You can forget about that in a couple of days. Right. Yeah. Oi, why R? No, it's L. Why? I don't understand why R appeared. L, of course. Then it's also periodic. Periodic because cosine is a periodic function. It's also periodic. So, for example, R at 0 equals to R at 2 pi, because cosine is a periodic function. So, what else? Okay, so now, that is the equation. Of course, with this epsilon, it should be, yeah, we know it should be an ellipse. But right now, at least for me, it's not obvious. Right? I want to not rewrite. Yeah, I want to write that trajectory in Cartesian coordinates because I'm well familiar with equation of an ellipse in Cartesian coordinates. Let's switch to Cartesian coordinates to see exactly where the ellipse is going to be, how it is going to be oriented, where the center, because right now it's not obvious. So now I will put a small bullet, and so let's switch to xy to see that ellipse. Okay, so now I will probably move a little bit faster because now it will be just simple algebra. So first, let me rewrite that equation in this form. So I'm going to have what? R plus epsilon r cosine phi equals to c. So I just multiply numerator and denominator. And obviously, you see, this is x, right? And so let me write it like this. So r equals c minus epsilon x. And the whole thing I want to square. So this is epsilon x, and I moved it to that side, and now I want to square the whole equation. When I square the whole equation, I will get r squared, which is x squared plus y squared. You remember we have two-dimensional problem. We're just moving from polar coordinates back to Cartesian. So this will give us x squared plus y squared. And that side, of course, we will get c squared plus epsilon squared x squared minus 2c epsilon x. Whew. Now let's combine, let's move everything which has variables to the left-hand side. Only constant c I will keep there. So this and that can be combined. So we'll have x squared 1 minus epsilon squared plus y squared plus 2c epsilon x equals to c squared. Simple algebra, just keep moving terms. Now, I don't want to have this factor in front of x squared. Let me just divide the whole equation by 1 minus epsilon squared. So as a result, I will have x squared plus y squared divided by 1 minus epsilon squared. Right? So you see I'm just dividing by this factor. Then that plus 2 c epsilon 1 minus epsilon squared x equals to c squared 1 minus epsilon squared. Whew. So now we will continue. Okay, we will continue introducing constants. You see this? This, I put it in a bracket, parenthesis. Let's call it D. But before I call it D, let me check to make sure that I don't make any. Okay, no, that's good. That's exactly. So let's call it D. And over here, probably above this, I will write D equals C epsilon over 1 minus epsilon squared. Let me frame it, because we will introduce lots of constants of this type. So now let me rewrite it. So it will be x squared plus 2dx. And you see immediately, we can complete a square in x. So if I over here add d squared, so I can create x plus d to the power of 2, right? So let's do it. And of course, on the right-hand side, I will also add d squared. So plus d squared, and then this y squared over 1 minus epsilon squared. And again, in order to make it correct, I will also add d squared to the right-hand side. So it will be c squared, 1 minus e squared plus d squared. So now we can complete a square. I can complete square over here. So it will be x plus d to the power of 2 plus still this term. And so if you take this, the value of d, plug it there, combine with this term, right? With this term, I'm not going to do it. It's very simple, half a line calculations. You will end up with this. I will just rewrite from my notes. So when you add these two terms, where is it? So you will end up with, it is equal to c squared 1 minus epsilon squared to the power of 2. So if you add these two terms, you will end up with that. And now it's time to introduce a new constant. This without squares, a. Let's call it a. So now let me introduce, so a equals, again, by definition, 3 lines. It's a c over 1 minus epsilon squared. So another constant. So effectively this, not effectively, this is a squared. And you see we're almost there. So now let's divide everything by a squared. We will get x plus d to the power of 2 divided by a squared plus y squared a squared. Okay, you know what? It overlaps with y upstairs, right? Let me separate them. A squared 1 minus epsilon squared, and it is equal to 1. And now you see we need to introduce the last constant, most likely. So let's call this as b squared. So now we can introduce b. So b equals, again, by definition, 3 lines. It will be a times square root of 1 minus epsilon squared. So how many constants we introduce? 1, 2, 3, 4, 5. Okay, it's not that bad. It's only 5. Okay, and so the final form of the equation, x plus d to the power of 2 divided by a squared plus y squared divided by b squared equals to 1. All right, so let's frame, because we got the equation of an ellipse, and effectively, we just finished proving Kepler's first law. Got elliptical orbit. All right, so it's basically Kepler's first law. Okay, let me write that down. So it's Kepler's first law, right? So about elliptical orbits in case of the gravitational force, right? Okay, the meaning we will understand. I will write that down in a second. Let's plot it. And first I usually ask, of course, when we have normal semester, is this equation written in canonical coordinates, or is this a canonical equation of an ellipse, canonical form of an equation of an ellipse? And it's not. I'm surprised usually students don't know these terms, canonical coordinate system, canonical equations, right? If, for example, ellipse has the simplest possible form, x squared divided by a squared, y squared divided by b squared equals 1, that's the canonical form of the equation. And that it has that form only in canonical coordinates. If you take your coordinate system and slightly tilt it, you will get a bunch of cross terms. The equation will look so ugly, you will never be able to even recognize the equation of an ellipse unless you run a bunch of tests, which is done usually in analytical geometry. Okay, so let me move here. And first I will, of course, remind you about canonical form, and then of course, we will plot this. Yeah, I need to. Wait. Okay, I have it in my notes. You have in your notes this c constant and epsilon, so we can restore it. Right. Yeah. Let me first remind you what is canonical. So, canonical equation of an ellipse has this form. So x squared over a squared plus y squared over b squared equals 1. But in our case, we have x plus d. It looks like, not it looks like, it's obviously, so that our ellipse is shifted along x direction relative to the ellipse in canonical coordinates. Okay, so in this case, ellipse looks like this. Okay, so let me draw first an ellipse, right? And the origin of canonical coordinates is at the center of an ellipse. So let me draw it here. So this is x and y, and this is canonical coordinates. So these are canonical coordinates. So canonical coordinates. So in canonical coordinates, equation of an ellipse has the simplest form, which is called canonical. Right. But in our case, it's slightly distorted form of the canonical equation, right? So, and obviously, it is shifted. So the origin is shifted to the right by the distance d. By the distance d. So let me now draw a bigger picture with the correct coordinate system. And I will probably start with an ellipse. So our ellipse, and I will draw it here. So, okay, probably I will be able only to finish drawing and analyzing it. So, no, first ellipse. Okay, good enough. Yeah, so the center of an ellipse is somewhere up here, right? And of course, canonical coordinates will be here. Okay, let me use some dash line. Right, so it's at that. But our origin is shifted, and our origin is over here, shifted by d and coordinate system. This is y, and this is x, right? And then our mass, our object with mass mu is, for example, here. So this is r, and this is angle phi. And you remember, we turn our coordinate system so that initial angle equals 0. As a result, we ended up basically with this coordinate. All right. Okay. So now, yeah, what is important that this distance is d, right? Relative to the canonical coordinates, our origin is shifted by d. So let's try to understand what is d. It's this constant, this constant. So meaning of d. And let's recall the focal distance. Or maybe, you know what, let me start with definition of d. No, let me remove the recall. Let me start from the definition of d. It's c times epsilon divided by 1 minus epsilon squared. So c over 1 minus epsilon squared, it's a semi-major axis. So it's equal to c times a. And again, now if you recall properties of an ellipse, c, okay, not c, hold it. Okay, a, it's a, okay, I started rushing myself and started making silly mistakes. Okay, this is, okay, let me slow down. So this is our a, and then, because I'm looking, no, c is not, shouldn't be here. So epsilon eccentricity is here. Eccentricity times a. So now, if you recall properties of an ellipse, epsilon times a, eccentricity times semi-major axis, it's a focal distance. F, which is focal distance. So d, it's actually focal distance. Probably I should have used the F symbol immediately from the very beginning, but I just followed the book, so. All right. So this F is focal distance, and it means that this point is one of the foci points. It's a focal point. So as a result, it means that this is a focal point. And so the center, force center is at the center, at the focal point. And of course, for the solar system, this is the position for the sun. You can say, how come? Right? Because you remember, where is our origin? When we were modifying Lagrangian, you remember we moved the origin at the center of mass, right? At the center of mass. And if you have a solar system, sun and the earth, of course the mass of the sun is way, way, way larger, right? And of course the center of mass point for the system sun, earth is inside of the sun. That's why the sun is at the focal point. And of course, mu is the reduced mass. And again, in the case when one object is much, much heavier, like the sun relative to the earth, reduced mass equal to the mass of the smaller object. So this is basically, for the solar system, mu is the mass of the earth. So that's basically the picture for the earth orbiting around the sun, or Venus or Mars, whatever, right? All that applicable. All right, so now we know the meaning of d. It's a focal distance, so we prove that the sun is at the one of the foci points. Then, of course, this distance is a semi-major axis, because we know the properties of this equation. Then this is semi-minor axis, b. So yeah, this is d. Right, so just meaning of all those constants. Then epsilon eccentricity, we know that. Now, what's the meaning of c? Over here at the very beginning, I introduced c. And so far, we have no idea what's the meaning of c. So let me, again, meaning. Okay, in order to see the meaning of that, okay. So the last stretch, guys. A couple of seconds. So in order to get the meaning of c, let's use equation of an ellipse in polar coordinates. So that r equals c divided by 1 plus epsilon cosine phi. Okay, so what if phi equals to pi over 2? If phi equals pi over 2, so we're going to get cosine pi over 2 is 0, and as a result, r at pi over 2 equals to c. So the constant c is just this distance. So that's where angle is pi over 2. So this distance is c, position over Earth, over planet, when the angle is pi over 2. So now, I think that's it, right? So basically, yeah, we proved Kepler's first law. All right. So now we proved Kepler's second law, Kepler's first law. Now, next class, quickly, I need to prove Kepler's third law. And we will look at unbounded orbits without actually getting through this derivation, because for hyperbola, it's kind of, again, similarly challenging just in terms of algebra, so we're not going to do it. So it's just maybe like 5-7 minutes of extra time on Tuesday, right? On Tuesday to finish this, and then non-inertial reference.